the next presentation dealing with the topic high temperature membrane electrode assemblies from Advent Technology. And your presenter is the Chief Technology Officer from Advent Technologies, Dr. Emory DeCastro. Give him a big hand, please.
Well, it's a pleasure to be able to talk about Advent Technologies in this relaxed setting. And let me get to the next slide. And we'll start actually with a little bit of a background of Advent Technologies and their high temperature membrane electrode assemblies. Oh. Okay, we're going fast. So let's start with the beginning. Advent's main business is the materials that make energy possible, hydrogen separations, and actually plastic photovoltaics. Today, our headquarters are in East Hartford, Connecticut. We have R&D activities in Boston and also additional R&D activities in Boston and Patras, where also we have pilot manufacturing of our high temperature membrane electrode assemblies. The company actually started with an idea, a simple idea. What would happen if you pushed polymers to their limit where they were stable at higher temperatures and highly corrosive acid environments? This idea was funded by the European and Greek grants and actually developed at the University of Patras in their polymer department. And they actually came across a material that was indeed very stable, and they developed a partnership with the electrocatalysis laboratory, Forth, and made a high temperature membrane electrode assembly. From this idea, additional investment was gathered. A company was founded, Advent Technologies, in Patras, Greece, 2005, and then shortly thereafter became incorporated in the United States as we moved our headquarters there. So why high temperature? Why even move into this market? The current slide actually gives you a good sense of the market space for high temperature. And it's really divided into two zones. One, very hot or relatively cool, very large systems or relatively small portable systems. And what you can see is that typically for most of the hot systems, very hot systems at 500 to over 1000 C, they're typically very, very large. With the exception of solid oxide, which is starting to get smaller now. When you think about the smaller scales of under kilowatts to tens of kilowatts, that's typically dominated by PEM fuel cells, largely because of their performance, but also relative ease of manufacturing. In fact, today, as you can see around here, established manufacturing for low temperature PEM. But between these two, between low temperature PEM and the higher temperature, there is still a need for ease of manufacture and high temperature that operates over 120 C and typically around 160 to 180 C, which gives you certain advantages. And so with this market in mind, Advent Technologies developed high temperature MEAs. This is what we mean by the need and by simplicity. For low temperature technology, as many as you may know, they can, when working on reformates, typically 10 ppm of carbon monoxide or less is about as high as they can operate at. They also need water to keep their electrolyte proton conductive, and so there typically is a balance of plant for the water. By operating at 160 to 180, you can eliminate these two components, so you have a far more simpler system. And it extends from there that simpler is also more reliable, right? Less mechanical systems. So higher HT PEM technology certainly improves PEM technology. With Advent, our primary product is the high temperature MEA, as it shows here in this stack. But this is also a nice reminder of the two products from a high temperature MEA. Naturally, it's electricity. That's what fuel cells are about. But it also produces very high quality heat. And this is what sets this PEM technology off from low temperature technology. Today, Advent actually has a family of high temperature PEM MEAs. They're used across various applications, from say small scale battery range extenders, from say 50 watts to 100 watts, that can recharge lithium-ion batteries in the field, auxiliary power units for trucks, stationary uninterrupted power supplies. By being able to reform liquid fuels with a higher energy density, you can get longer run times for backup power, to even micro-combined heat and power systems. We actually have two families of products. One operates typically around 160 C. The other one operates typically around 180 C. With both these products, they're still both based on advanced polymers, and phosphoric acid is the electrolyte, which means great resistance to carbon monoxide, also great sulfur tolerance as well. And last but not least, robust operation when your air feed has various contaminants that you can pick up from the air around you. So several advantages, but both products do that. And here are the two products. I think if you know Advent, you probably know very well about the TPS polymer. Operates between 120, 200 C, very good acid management, moderate proton conductivity, very rugged membrane, especially under a differential pressure. And as was shown here last year, next generation materials that can go above 200 degrees C. But here at the Hanover Fair, we're actually announcing a new product, and that's actually Advent's PBI-based MEA. Operates similar but a little bit cooler, up to roughly 180 C. Of the two, certainly the highest acid content. Proton conductivity a little bit greater, proven lifetime. But last and not least, based on licensed materials and processes from the BASF PBI. So a well-established product. So let's talk a little bit more about the details of these two families of polymers, these two families of MEAs. The Advent TPS is actually based on aromatic polyethers. This is what gives it the strength. These materials, as shown here in the green dots, have high thermal stability, high chemical stability as well, with regards to being stable in phosphoric acid. That is actually combined with pyridine polar groups, shown in blue here. This becomes the hydrogen acceptor site, basically a sponge for phosphoric acid to keep it within the membrane matrix, even at the higher temperatures. These materials are polymerized in a polymerization. That resulting powder is then formed and cast into a film. It's solvent cast into a film. That film is then imbibed into acid and forms the acid-containing membrane, then eventually combined with electrodes. Again, as mentioned last year, the group at Advent has continued to advance this chemistry. They have introduced some cross-linking behavior into the polymer. What this does, it actually allows you to operate at even higher temperatures, which means greater CO tolerance. It actually has improved the mechanical and chemical stability. And a nice fringe benefit of being able to operate at 200 or 220 is that even more improved thermal integration with some of the other subsystems within the MEA, within the stack and balance of plant systems themselves. So as we show here some of the characteristics of the cross-linked, I'll point out the second point, thermal stability. If you heat that to 450 degrees C, you lose only 5% of the initial weight. Very high conductivity, which certainly is partially imported because of the acid in the structure, but also because of the higher operating temperature. And lastly, still very good doping levels of acid. If you were to compare this cross-linked to the standard, you can see here it shows a little bit more how the glass transition temperature has moved out to 280. The weight loss that I mentioned before at 450 compares favorably to the 415. Conductivity, again, a little bit greater. These results at 220. And you also then get a boost in the kinetics, and you get actually a voltage boost as well by going to the higher temperatures, thus a little bit greater efficiency from the electrical standpoint. Okay, now for the other product that we announced, the PBI-based one. And for those of you that know about this chemistry, I will lead you through. It's really a little bit different sort of chemistry. And the process begins with two monomers, typically a tetramine and an aromatic diacid. These are dissolved in what's called the reactive solvent, polyphosphoric acid. Once this is heated up, you begin the condensation reaction, water is removed. You actually then form the PBI, which is soluble in polyphosphoric acid. That material is then cast. It's cast onto a carrier. It is still in a very viscous state, and it gets hydrolyzed. Once the polyphosphoric acid changes to phosphoric acid, the phase of the PBI changes to a rugged plastic. And that's what forms the membrane. That equilibrium is shown here. And it's really the equilibrium that really defines how the MEA works. It defines the limits of the operating temperature for the MEA. And also defines of why it works. So we actually start with the polymer film casting in this loose sol state. When we hydrolyze, it goes to the gel in a membrane. And then the key is to operate when it still remains in the gel state. So it's actually a phase change that makes this polymer so important. Okay, then the next part about the technology that Advent also is developing from the BSF license is actually gas diffusion electrodes. Many here know about their MEAs from coating membrane directly with catalysts. In fact, the prior talk, there was a great example of using ultrasound to lay down a layer on a membrane. But within this process, if you would imagine taking a substrate with a microporous layer and then coating that with catalyst, you can do that actually at very large volume at relatively high speed or low costs. That material that can then be cut into smaller pieces and laminated to your membrane. And in fact, that's exactly what happens for both the PBI-based MEA and the TPS-based MEA. And so this catalyst-coated microporous layer really offers potential for low-cost manufacturing. Now, once you have your membrane issues solved, when you think about the job of the membrane, it's relatively simple, right? It's the gate for the proton. When you think about the job of your electrode layer, it's actually very complex. You have to maintain a three-phase layer. You have to use your catalyst wisely. So in fact, once your membrane material issue is solved, the greatest value of your membrane electrode assembly is in the gas diffusion electrode. This is also your major contribution to the final power you obtain. And typically, assuming you have a stable membrane, it's your rate limiting step or your lifetime limiting step for durability. So within the process that Advent has licensed from BSF, we then use this GDE technology. It's a roll-to-roll coating technology, moderately high speed. The inks are actually very stable. They produce very uniform coating. It's actually been a proven technology. I'll show you some examples of that coming up soon. It employs statistical process control to maintain high quality of the coatings, and it certainly uses an alloy at the cathode. In fact, this coating process actually won an award by the Department of Energy last year in 2013 for manufacturing R&D. So I mentioned statistical process control, and so let me lead you through this a little bit. This will take a little bit to go through. But basically the approach is this, and what I have here is an example of the cathode. So I'll focus on the cathode. Basically, roughly 2,000 square meters of gas diffusion electrode were created in various batches. This was sampled over 360 times using 45 centimeters squared sample size throughout these rolls of material. These are then averaged. We get a polarization curve run under standard conditions, 160 degrees C, hydrogen and air. These are then constructed with an average, which gives us the blue line. And then we here have plotted plus and minus 3 sigma to create our control zone. Now we start with a new batch, gas diffusion electrode. We compare that against our control. Now typically, most people would just compare average to average and say, is it above or below? But the process we use actually incorporates not only averages, but variation. Because in the manufacturing environment, you need to understand your variation and make sure that materials with either high variation or low quality are not released into the MEA manufacturing line. And so I'll go through an example here of something that failed. So the way we construct pass or fail is that we take the new material, which is shown the average of several samples of a new material, gas diffusion electrode cathode. You construct an average, which is shown in the red line. But then we subtract from that average 2 sigma of the variation of those samples. And what we have shown here is actually 1 sigma, or plus or minus a range of 2 sigma. And what you can see, it may be very hard from the back row, it's probably even hard from the front row, but the average minus 2 sigma of this material would actually make that failed material. So without even looking at this plot, let's just visualize 2 situations. You could have a test material that has a very high average, even a higher average than your standard blue line. But if the variation is great, there's a chance that material with low performing would get released into production line. So high variation, high average, you could still possibly reject that. The other case can exist as too. You could have a relatively low average, something just below the blue line, but very tight and uniform variation. And so that would actually be a pass. You would accept that material because you would be very confident that you have not released off-spec material. And so this is a great part of the technology that we've obtained, is these very advanced electrodes and very solid statistical methods of keeping them, the quality, under control. Okay, let's talk a little bit about the future. With regards to membrane development, the TPS, which is really the hallmark product of Advent, that actually is a well-defined process. It's actually cast today in a roll-to-roll process. And so as market demands, we will scale that up. That's a relatively simple task. The cross-linked, which is still today in a developmental scale, that's called the Advent TPS 200X. Luckily for that, the manufacturing process is very similar to the TPS. And so once we finish our developmental cycle, we'll go to a roll-to-roll cycle for that. We expect that jump to be relatively straightforward. And then lastly, there's the PBI product, which is not standing still either. And as improvements come from the supplier, those will be incorporated into next generation products. With regards to the electrode, there are really 3 focuses: quality, durability, and cost. On the quality side, our first job is to adapt these BSF gas diffusion electrodes to the Advent TPS MEA. We expect that to be a next generation product coming out within 6 months. With regards to durability, our next task is to identify corrosion-resistant catalysts. We have some of those on the boards. Develop coatings based on this licensed coating technology, and develop electrodes from them. Last is the cost. Here we'll be moving towards the paper-based substrates, as well as working on reduction of precious metal content. And I'll show you 2 examples of that, more proof of principle. This is an example of coating a paper substrate, more of a proof of concept. The gas diffusion electrode technology I mentioned before is based on carbon cloth, inks. It was a multi-step process. The drive here, or the goal here for coating the paper substrate, is to get down to essentially 1 coat for the catalyst layer, so a single coat. And what we show here is actually proof of principle. So the line in the middle, which is really overlaying the average line of the cloth, is a single coat of catalyst layer on the paper-based substrate that has a microporous layer. We see no loss in performance, and it certainly, obviously, makes the MEA thinner by roughly 25% with the paper-based coating. So nice proof of principle of the direction that we'll be going in. The second part, called precious metal thrift, reducing the precious metal content. In fact, the results of this test were even a surprise to us. But let's back up. I had mentioned before about these very uniform coatings. What uniform coatings really mean, sort of the code word for that, is high utilization of your catalyst. That is, the catalyst that you're coating is going down uniformly, the additives are distributed uniformly, and so you have the opportunity to utilize that catalyst more effectively. That's exactly what this plot shows. In fact, the blue line on the top is an anode structure with a 30% reduction of precious metal compared to the control, which is shown here. Our goal, our expectation, was to have the exact same performance. But what you can see is the performance increased. So not only did we utilize more effectively the catalyst in that structure, but we created a better structure for mass transport for Reformate to get in there. So certainly a good direction to go for reducing precious metal. So in conclusion then, with regards to the product portfolio of Advent Technologies, we have the Advent TPS MEA, certainly a very robust platform for the highest operating temperature. We have the Advent PBI MEA, highest acid loading, proven lifetime in the field. And then we also will be offering gas diffusion electrodes as well and TPS membranes. And the plot on the right is a nice illustration of the impact of temperature with regards to the PBI system, TPS system. And you can clearly see that with our voltage at 0.2 amps per centimeter squared, partial pressure of CO from 1 to 3%, that as you go to the higher temperature, you can operate with higher levels of CO. And with that, I think we certainly have time for questions and to refresh your refreshments. Thank you.
Thank you very much. Yeah, thank you very much for this informative, interesting presentation here on stage today.